Check. Okay, welcome to the class meeting 9. By the way, I'm going to assign a kind of homework, or you may regard it as a take-home exam. And you are going to return it next Monday. So you will have enough time to manage the holiday and your take-home exam. So I will send you an email through PLMS when the problem set is ready. Got it? Okay, so last time we studied this paper by Gardner and Franks. By the way, William Gardner is again. Okay, just a second. It's Monday, right? Okay. Okay, where is the system display? Okay, let's share it again. So does it work now? Okay. So William Gardner is a kind of father of cyclostationarity. So he published many papers related to cyclostationarity, and also he was the editor of an edited book entitled "Cyclostationarity in Signal Processing." So, if you search, for example, Amazon, let me do that. And if you type in cyclostationarity, then you will see some books, recent and old. And this is the book I mentioned, Cyclostationarity in Communications and Signal Processing. And this is very old book, so it kind of compiles important papers related to cyclostationarity in communication signal processing up to 1994. And then there has been tremendous interest in exploiting cyclostationarity in signal communications because direct sequence space spectrum is strongly related to cyclostationarity. However, the discussions in that area is kind of far off from the tradition exercised in this area. So unfortunately, there was the kind of a tree for cyclostationarity, and there was another tree for direct sequence space spectrum system, but the trees were not totally combined. There was some attempts to combine these two, and on that small area, I contributed a little bit. So you will see the papers on the intersection of cyclostationarity and direct sequence space spectrum later, not today. Anyway, and as you see, another book is written by Antonio Napolitano, and he also published another book, as you see here, Cyclostationary Processes and Time Series. He not only published this one, and also he published other books, I remember. But interesting thing is that this book, Generalization of Cyclostationary Signal Processing, is kind of related to spectrally correlated random processes theory. Got it? So if you want to see a kind of a single authored, very logically organized book, then look up these two books. But if you want to see the kind of tradition and root and how people develop the basic ideas, then this kind of edited book is a good choice. Got it? Okay, so yeah, this is interesting, characterizing cyclostationary features of digital mode with what? Empirical measurements using spectral correlation function. Probably I'd better read it. I didn't know the existence of this book, published May this year. So could you, one of my RA, order this book using our project fund? It would be very interesting. Probably we have hardcover, right? Yeah. It's not that expensive. Interesting. Anyway, so last time we studied so-called harmonic series representation. And what was that? It was related to rewriting a single cyclostationary random process as a kind of weighted sum of jointly wise and stationary random processes. However, the weights were time-varying functions with different frequencies. So as you see here, this one is a weight. So there are two ways to understand the harmonic series representation of a cyclostation random process. One is to see it as something similar to Fourier series. So in that case, these jointly wise and stationary random processes are kind of Fourier coefficients. And you have harmonics, right? And another one is that you have weighted sum of jointly wise and stationary random processes, where weights are time-varying functions, especially harmonically related tone signals with equal spacing. Got it? So whenever you have such summation of products, then you have two ways in interpreting the ideas. So let me write it here. So it's like, suppose you have X equals A transpose B. Sorry, X scalar. Got it? And this is nothing but sigma A sub I, B sub I. If you have complex valued vector, then you have conjugation, right? And this sum of products, so this is a sum of products. Whenever you see this form, try to rewrite it as a vector-vector multiplication form, or sometimes scalar vector, sometimes vector scalar form. And then also try to understand this one as weighted sum of B sub i's, sometimes weighted sum of A sub I conjugates. Got it? By doing that, you can better understand what's going on. And sometimes one interpretation gives you a better understanding and better interpretation of the representation. However, the other representation also, in other cases, serves very well for other purposes. Got it? So this is very important trick you must be well equipped with as a communication engineer. Anyway, so as you see here, the harmonic series representation allows you to rewrite a single cyclostationary random process as a weighted sum of jointly wise and stationary random processes. And last time, I've little bit exposed something interesting, and that was the relation between cyclostationary random processes being filtered by a periodically time-varying linear filter. And if you use harmonic series representation of the input and the output of this linear periodically time-varying system, then what do you have? In terms of the output of the vectorized Fourier transform of the input and output, you have a multi-input, multi-output system. So this figure is what you need to remember. Okay? So as you see, cyclostationary, cyclostationary. Of course, you don't need cyclostationarity for the equivalence of these two, but joint cyclostationarity of the elements of the input and the elements of output are only guaranteed when you convert these two signals using a vectorized Fourier transform with period in frequency domain 1 over capital T, or in time domain capital T, which is the same as the cycle period of the input and output. Ready? So by doing this, actually, we can utilize a lot of interesting geometrical interpretation of the filtering, such as eigen decomposition and singular value decomposition, as you will see later on. Got it? So anyway, so as I told you last time, I'm not going to cover the translation series representation at this moment, because we are going to be back on that topic when we study the spread spectrum system and cyclostationarity. So today, we are going to see more similar paper to this 2004 paper we've covered. And this was published in 2010, and the title is the optimal orthogonal overlay for cyclostationary legacy signal. And you will see that the signal model is almost the same as the paper published in 2004, except that we have one additional constraint. So let's see. By the way, whenever you see a paper with a title that is not familiar with you, then divide the title into words and try to understand what does that mean. First one is overlay, probably, and second one is legacy. And this is all related with spectrum sharing. In Korean, 주파수 공유. And why this concept is very important? Why this spectrum sharing, concept of spectrum sharing, very important in communications? It's because in communications, in many cases, we are interested in not just electrical communications, but radio communications, where we utilize radio wave to transmit our information. And what's the property of radio wave? It's a wave that can propagate through the air, even through the vacuum, with very high speed. And in free space, what is the received signal power at the distance with R meters? In free space, we know from high school math that the received power is proportional to the transmitted power times distance squared in free space, because we approximate the source as a point radiator, isotropic radiator. In that case, each shell of a sphere with different radius must have same flux of power outgoing. So as the distance increases, the area of surface increases as a square of the distance. So the power density is inversely proportional to R squared. And compared to radio communication, actually radio wave over free space and radio wave over RF cable, you can compare. And actually, through the RF cable, we transmit a radio wave, precisely speaking. However, in general, we do not say that we are transmitting radio wave. It's somewhat strange, but actually, we are transmitting radio wave. Now, what happens in RF cable? Suppose you have an RF cable of length some L meters. Then usually this cable has what? Has loss factor, or loss factor in terms of negative something something dB per meters. Why do we have this one? Why do we have this one? Suppose we serially connect the unit length cables. And if the input is P, then output is what? P minus XX dB. Now, this goes in, and what would be the output? P minus 2 XX dB. In this way, as the length of the cable increases, what happens? In terms of dB, your received signal power linearly decreases. However, in linear scale, what does that mean? Your received power exponentially decreases. So what is interesting is like this. From the source, suppose you have two links. One is radio wave link through air, and the other is the cable. What will happen? Because in cable, your radiated signal or input power is just linearly decreasing as the distance increases in terms of dB. But in radio communication, you transmit signal through antenna, but only small portion of the power is received at the antenna. So from the beginning, you have significant difference. So suppose this is 1 meters. I'm going to use logarithmic scale. This is 10 meters, 100 meters, 1,000 meters, 10,000 meters, something like that. And also, let's see this in dB. And suppose this is 0 dB. And in cable, you have that XX, negative XX dB per meter. So since this is 1 meter, so you have here. But in radio communication, even though you have just 1 meter, received power is much attenuated because you have very small effective aperture of the received signal. And this antenna, even though in reality this is not an isotropic antenna, it wastes a lot of power. So you start from around here, some negative 30 dB, for example. Now what happens? Now what happens? This is almost an affine function. However, this one is a waterfall curve, as you've seen in dr versus EB over N naught for the cube function. So what does that mean? If you have some threshold, if you set, then this transmitting radio wave is much more power efficient than using a cable. Of course, this is half true and half not true, because in using cables, actually, you can use what? So-called repeaters that amplifies the signal and retransmits. So this is kind of drop and suddenly up, drop, something like that. Got it? So be careful, be careful, okay? Anyway, what does this mean, by the way? If you transmit radio wave, you don't need repeater. It decays very, very slowly. Actually, whenever you see a straight line with some slope in the log-log plot, you have a power law that governs the phenomenon. Power law means that something is proportional to some parameter, negative squared or positive cubed, something like that. In this case, r to the negative 2. Got it? So what happens in radio communication? From the beginning of the radio communication era, we suffered from interference. So it's like, suppose I cannot draw the Italian peninsula, but suppose this is Italia, and suppose this is Marconi's home. I don't know exact place, and he developed the very primitive radio transmitter and receiver. And what will happen if he increased the power? That propagates a lot of the distance. And suppose there is another guy who wants to transmit a signal in almost the same band. They interfere each other. Actually, in the early period, there was no bandpass filter in communication system. Suppose you have AM receiver. You all know what is a amplitude modulation. Suppose you have AM receiver, but you don't have frequency selective filter. You receive hundreds, not hundreds, suppose 10 AM radio stations. And you just apply the signal, which is the summation of 10 radio stations, however, whatever difference they have, into an envelope detector, or that rectifier. What will happen? You will have summation of 10 voice signals, right? So your communication fails. That's what happened. So the very scarce resource, which is the spectrum, has to be shared in some way. So spectrum sharing in some way was the fundamental problem from the beginning of the radio communication. And now we have more and more radio devices, not only radio communication devices, but also radar systems or some sensing systems. However, we are running out of the spectrum band. There are much increasing demand, but resource is limited. What will happen? We need a clever idea to solve the problem. And that's why we now have a cellular communication system. That is one of the most important breakthrough in spectrum sharing idea. And here, the spectrum sharing is another kind of very limited scope we are considering. So it's like this. Suppose this frequency band is already assigned by the government or some organization for some special use. For example, cellular communications for 5G. So this is assigned. Now, this occupies, for example, in Korea, around 300 megahertz, more than 300 megahertz, very large. And people monitor the utilization of this spectrum and found that it's not fully utilized, which means that they monitored the signal power in the air, throughout some finite period, 30 days, 40 days, 100 days, one year, 365 days. And they find what? For example, in the midnight, many people sleep. What does that mean? They do not communicate. So spectrum is very rarely used. But the cellular service provider like SKT, KT, and LGU Plus already paid a lot of money to auction the spectrum to the government. They paid a lot of money. So what do you want to do if you are the CFO or some CXO of these three companies, right? If the government allows, probably you want to let some people to utilize your spectrum and paying you some money as a kind of reward or repayment. So here goes the idea. So you have three companies, signal already occupying here. Let's say that this is SKT's band. And these signals now serve as so-called legacy signal. Now, you are going to put some radio signal there in the band and simply divide. There are three ways to put signal. First one is underlay. Second one is overlay. Third one is interweaving. And as the name says, underlay means that your new signal goes under the legacy signal. What does that mean? Legacy is the most important signal. And your signal must not interfere the legacy signal's original purpose, whether it is radio communication signal or a radar signal. Then what would be overlay? Overlay is that you are the most important one. Your performance metric is important. Got it? And third one, interweaving, is that you are going to use the spectrum, but what you are going to do that is not just underlay that looks like very small noise to the legacy system. It's not a very high power overlay signal, but you utilize the spectrum in the frequency domain and time domain so that, for example, you do not transmit whether the legacy signal is transmitting. It could be performed in time domain, so which means that you sense whether the legacy systems are transmitting or not, and you believe they do not transmit, then you utilize the spectrum. And in the frequency, because this frequency band is very large, for example, in 5G, 100 megahertz, and due to the slicing of the frequency band, some of the subcarriers may be only utilized at some time period. Then you utilize that part in the frequency domain. Or even you can spatially utilize the entire spectrum or some part of the spectrum, because, for example, in the downlink transmission, usually only the base station is transmitting to the user equipments. Then you, for example, transmit at that period to your designated signal using a very focused beam, which do not interfere with downlink signal. Then you can kind of interweave your signal without much interfering to the legacy system's operation. Got it? And in this paper, it's overlay. So it's not going to much care about the legacy signal, legacy system's performance. However, it transmits very similar way to interweaving by orthogonalize its signal in some way. So when this paper was submitted, some of the review I remember questioned whether the title is correct or not. Is it underlay? Is it overlay? Something like that. However, the reason why I and the co-author titled this one as overlay is that we are kind of transmitting with our full power. So our system transmits at the full power given as our constraint. In that sense, this is a design of overlay system, but cleverly avoid interference to the legacy system. Got it? And of course, this one, if you see the signal model, this signal model is very weird. It's like the new system transmits its own receiver, but at the same time, it has some information about his signals, amount of interference at the legacy receiver. And I'm not quite remember whether we fully discussed that possible scenario here or not, but if I remember, I explained it to the reviewers about what kind of scenario this could be. So let me give you the idea first, because you may have some strange feeling about that. Suppose you have a satellite. And this is ground station for the uplink. And suppose this is a broadcast satellite. Then this information is going to cover some area. And we are assuming that this ground station is equipped with our transmitter and also the receiver for the downlink. And when it is possible, for example, in TV broadcasting. So you have satellite setups. Set-top box. Is it set-top box? Yeah. So you have, anyway, satellite broadcasting receiver. And that is manufactured and distributed to the subscribers. And this is, if this satellite is a geostationary one, then it's around more than 30,000 kilometers away from the surface. So if this is 6,000 kilometer radius of the Earth, 1, 2, 3, 4, 5, and 6, very far away. And its beam is focused on the Korean Peninsula. For the direct reception, you may assume that most of the receivers are almost identically performing. Got it? So the idea is initiated from the fact that how can we utilize the, for example, very scarce satellite, for example, satellite communication band to kind of put more signals so that we may increase the spectral efficiency. Got it? So in this scenario, original broadcasting signal is legacy transmitter. And these are legacy receivers. Of course, there are many, many legacy receivers possible, but in this case, you may assume they are identical. And now what happens? This system not only overlays the signal, it also receives the signal, so it can monitor the performance of your set-top box. So in this way, some strange idea may have interesting application. Got it? So here goes the abstraction of this system. So you have legacy transmitter. And in this case, for the generalization, we considered capital K legacy transmitters and capital K legacy receivers. Am I right? Yes, legacy receivers. And this is our kind of overlay transmitter. And this is overlay receiver. And this transmitted signal passes through some case channel. It could be identical, almost identical in this satellite communication scenario. But we assumed very general linear time invariant system. And this is the linear time invariant channel from the overlay transmitter and receiver. And this is the overlay receiver. And am I right? Yeah, I believe so. Yeah. And here we have something interesting. Even though the transmitter and receiver pair have linear filters, the output could be oversampled, because this oversampling is in many cases practiced for digital implementation. It could be here M sub k must be, by the way, T sub 0 is the common, if I remember correctly, common symbol period of the legacy signals, and M sub k are possibly different oversampling factors. Got it? And for generality, we put the delay of the signal. And this is because if we more complicated the scenario, there could be another station transmitting to this satellite, and summation of this signal 1 and signal 2 may occupy the same frequency band, which we are going to put our overlay signal. Got it? And these are all received at the same set-top box, so we may design this way. And many of you wonder why the receivers are almost regarded identical, because the signals are summed over here. They are summed over at the satellite and then amplified and transmitted through the downlink. So they are almost the same in different receivers. Of course, in Korean Peninsula, you know that some area is rainy and the other area may be very shiny, and we didn't consider that way, that scenario. Anyway, so we have multiple pairs of transmitter and receivers for legacy system, and we are going to put one overlay system. And the idea is that since we assume we know all the channels, what we are going to do is that we are going to null our signal by designing this S carefully, so that we want our signal become 0 at this output of oversampler. Because we don't know what kind of processing is done for the error control coding. We know that the set-top box has some fixed oversampling rate given a specific model of the set-top box, something like that. Got it? And here, the interesting idea is this one. See that T sub 0 is assumed to be the common symbol period of linearly modulated signals of the legacy pairs. And here we have our system that has freedom in choosing our cycle period. It could be some integer multiple of the kind of base period. And you may wonder why this is necessary, but you will see why this is necessary for better performance of your system. Got it? So anyway, what is the result? So let's see the result first. Not good. Okay, good. So this is a very unorthodox performance curve. And some of you may say that it looks like a waterfall curve. It's not, okay? Even though this vertical axis represents bit error rate, this horizontal axis does not represent ES over N naught or EB over N naught. This is roll-off factor of the legacy transmit waveform. And you may say that, what does that mean here? And also you will see different curves with different legends. And why is it so? Anyway, we know that the lower the BR, the better the performance, right? So let's see, for example, some 10 to the negative 5 bit error rate. And this can be achieved by this curve that corresponds to that legend. And what does that mean? If you just take a look at the denominator, the symbol period is 8 times the base period. What does that mean? All the legacy signals has period, for example, this one. Means that one information symbol, QPSK or 16 QAM, transmitted, and transmitted. And what does this mean? Your overlay system has 8 times longer symbol period. So it transmits one symbol for 8 times T sub 0. So this system, overlay system, slowly transmits information compared to the legacy systems. What about that one? It's 4 times slower, 2 times slower, the same transmission rate. The problem of this one, if you have taken the information theory course, is that, okay, symbol transmission rate is slowed down, but if we have finite transmit power, what does that mean? Symbol energy is increasing, even if we slow down. In that case, we may increase the constellation size of modulation order of each symbol to compensate for the slowed down transmission rate. Because this slowed down rate is what? Symbols per second. Now, you may increase bits per symbol by choosing different modulation order, as you do in 4G and 5G cellular systems, where you have a table of MCS, modulation and coding scheme, where sometimes you slow down, you increase the constellation size, or sometimes you slow down and also decrease your modulation order so that each symbol has more energy per bit so that you can meet some BR requirement for successful decoding of the information symbol, something like that. So this paper is kind of not complete, because whenever you have given power and freedom to change the symbol transmission rate, you also have to incorporate the modulation order for a fair comparison. But this paper has limitation in that it does not talk much about that part. It only talks about, okay, suppose we slow down and we may improve our signal to interference ratio at our desired receiver. Got it? So, as many of you already know, in communication system, not only a small part of the system needs to be improved, but the overall system performance needs to be improved. In that case, you have to think about the overall information rate. The problem of modern digital communication is this one. Long ago, the performance metric was very simple, because using our cellular system, we wanted to convey our voice signal only. Even if we modernize our civilization in an exponential rate, we have muscles connected to tissues and masses, right? We cannot speak fast. We cannot increase the frequency of our vocal cord. So in many cases, in the pre-3G system, we only consider a single performance metric, voice quality of the core. Now, as you see, and as you know from the study of 5G cellular systems, now we are going to build a premium network, much premium than the ordinary internet, through our cellular system by providing much more freedom in the quality of service. Here, quality of service means that its performance metric can be very, very different. Long ago, as I told you in 3G or pre-3G cellular, voice was dominant, and we have almost single metric called drop rate, quality, blah, 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 bandwidth. But now we have different types of data. Sometimes we want very high quality voice. Sometimes we want very short message with very weak signal, but want that message pass through the system very reliably. Sometimes we want very small latency so that we can control some self-driving car at a remote distance with high computing power, something like that. And in each application or so-called use cases, we have different requirements. And that requirements must be, this is very weird, must be satisfied at the same time by what? By the system. So it's very hard to optimize our resource allocation. So actually, one excuse about this paper's obvious limitation is that anyway, no paper can handle all different possible quality of service requirements. And if you do that, Ericsson, Nokia, Samsung, Huawei will not be much happy if you publish that kind of paper, ultimate paper about 5G resource allocation. And no one can do that, but suppose you publish that one. And if I'm a Huawei CEO, hey, CTO, come here, sit. Okay, according to the paper, our system's performance is this lower than the optimal one. What's going on, right? Anyway, that's not possible. Yeah. It's a kind of resource allocation is one of the most difficult problem currently the human being has confronted. It's not just the simple Markov decision process that is very popular in reinforcement learning. Because the environment is not Markovian at all. Got it? So anyway, so even though the paper has obvious limitation, please forgive me. So I hope you understand the big picture of the scope of this paper. What are we going to do? We are going to choose the transmit waveform, the receive waveform of our overlay system, and also change, not optimally decide, just change our symbol rate and see what happens when we optimize these two filters in order not to interfere at all case receivers, which have receive filter and oversampler. Got it? Since we are running out of time, I'm not going to see the details, but I'm going to show some important performance metrics, and you are very familiar with this one. So again, we are going to minimize the mean squared error when we estimate the desired symbol. Got it? So Z of L is overlay system's L's output. That is going to be used as the estimate of the desired S symbol. So this is exactly the same as 2004 paper. Another same thing is the transmit power. And it looks different, but they are the same. So this is what? This is the signal. You may regard it as the input to the channel of the overlay or our desired system. And it's squared instantaneous power integrated over some period capital T and divided by the period. So this becomes the power over time T, and its ensemble average is taken, and this is given. By the way, some of you, and actually when I was a graduate student, I couldn't understand why we always have this kind of power limitation in radio communication. It's because we have what? We have power amplifier in our system. And of course, if we change our power amplifier so that we can emit more power, then we may increase this one. However, in many radio communications, the regulatory organization, such as Korean government or sometimes UN under UN organization, they have very strong transmission power regulation. Sometimes we have some choices of power amplifiers among possibly only a few groups. For example, in my lab, we do not build our power amplifier. We purchase from vendors such as mini circuits. And if we specify our desired frequency band, there are only a few choices for our power amplifier. And we see the how much distortion that power amplifier generates if we drive that power amplifier with some such dBm input power. And we don't want nonlinear distortion or distortion-induced spectral regrowth or something like that. In that case, we have power limitation. That's why this is one of the popular constraint in the design of communication systems. However, anyway, I can I can criticize myself, right? If this is other guy's paper and I criticize that one, and that guy finds my YouTube lecture, he or she will be very angry, but it's okay, right? Anyway, co-authors are my former RAs, and me, I myself is the co-author. So this has another problem. Why? It only takes care of average power, because the amplifier is not operating on average power. It operates instantaneous input. So suppose even though our average power constraint is met, but our peak power goes extremely high, what will happen? Whenever this peak occurs, our power amplifier will be driven into nonlinear amplification region. Of course, the power efficiency of our amplifier will be increased at the time. However, there will be clipping or distortion at the output of the power amplifier. That is bad for the reception. Another one is that whenever we have nonlinear operation, there occurs unexpected or incalculable nonlinear distortions in the frequency domain. Of course, be careful. Linear system also generates some spectral, undesired spectral transmission power. Consider modulation effect. Modulator is a linear system. So some frequency band that shouldn't have power shows some non-zero power. You must suspect first some modulation effect. That is a linear systems interference. Also, you have to consider some nonlinear distortion. So linear time varying system or nonlinear system may give you some strange spurious emission on some band where there shouldn't be that kind of signal power. Got it? Anyway, so this is a little bit okay performance metric or constraint in the design. The problem of peak power limitation is that it's very hard to handle in most of the cases, as many of you already know, right? Peak to average power ratio. That is also important. But what does matter is that the probability of the entire transmission go over some threshold in power, not just peak power's distribution. So it's not easy in general to analytically derive so-called instantaneous normalized powers distribution, empirical or theoretical. And in only limited cases, you can derive the CDF or PDF of the peak power given the observation interval. So it's a very hard problem. However, what's going on right now? This is the period of so-called AI ML models. And interestingly, they have solved many seemingly unsolvable problems recently. How? Before, we engineers wanted to linearize or kind of approximate nonlinear systems using linear systems or linear time varying systems so that we can use our kind of old school toolbox tools like Fourier transform of such and such. However, these days, what do? We build AI ML models, and we don't know exactly how it works. But we put a lot of data, for example, in the supervised learning, some pair of input and desired output, and then the system with a lot of coefficients kind of tries to approximate best that system. And sometimes the coefficients can be utilized to design the inverse system of that one. In that case, we may model nonlinear amplifier using neural nets. And using the coefficient, we may pre-distort sometimes the signal or remove the distortion in the receiver, something like that. So this handling peak power or distribution of envelopes is still a difficult problem, but we don't need to be and we shouldn't be frustrated because of the modern, very fast development of machine learning and AI models. The problem of these models is that it's very hard to analyze its performance. We can only show some examples, and many of the researchers may be very, very tempted by the evil voice saying that, hey, let's do cherry picking, something like that. And that's why I do not much believe the results using AI machine learning models in handling nonlinear systems. If you ask the reliability of these systems to especially control theorists, kind of old school control theorists, they will all dismiss the idea of using these AI machine learning models in designing control systems, because in the old school control systems, what is most important is what? Stability. And stability is not only not guaranteed in their system, in that kind of modern machine learning and AI systems, but can never be proved to be stable because they are nonlinear systems. So anyway, so never forget as an engineer that these modern tools are very, very strong and powerful new tools. So you, in your toolbox as an engineer, now you have very interesting tool. You know how to use it, but you know what will happen while you use it. So never forget that problem of your new tool. Anyway, so let me show you some difference between the 2004 paper and this paper in problem formulation. This would be interesting. So you've seen something similar in 2004 paper. Interestingly, this is the same, right? Decision parameters are the same, and even the objective function is the same or looks very similar. The difference is this one actually. And your constraint has the same constraint as before, except you have additional constraint. And geometrically, if you ignore this parenthesis of f, so as a function of f, if you just view this as a vector and matrix and vector, what is this one? It's kind of a vector and matrix vector product, which is vector-vector product. And that vector-vector product equals 0. What does that mean? Two vectors are orthogonal. That's why the title has orthogonal overlay. Also, we may call, whenever something equals 0, we may say orthogonal, and later we may justify our calling that orthogonal in our some geometrical interpretation. But you can immediately see why I and my co-author claimed our result is an orthogonal overlay, because as you see here, this is nothing but the orthogonality condition. You may see this as a vector for the case receiver, right? And this is desired signal. So our desired signal is orthogonal to the case receiver convolved with case filter. Got it? And that holds for all k. And also for all oversampled outputs. So we have kind of complicated many constraints. Got it? Okay, we have 8 more minutes. Yeah. By the way, also, this paper was under development of our ideas. And let me show. So let's see this strange plot. And here we have B sub R, some band subscript by R, some band subscripted by T, and some band subscripted by H. What does that mean? And at that time, more than 15 years ago, we confronted some problem. Because suppose your entire frequency band on which you can transmit your new signal is actually utilized by different signals and pair of receivers. So for example, the first one, second one, and third one, and fourth one occupies your band. And you are allowed to utilize all of them. But each one has its dedicated signal frequency band and also some receiver band. And there could be possibly this third band is prohibited to be used for you by yourself. It's possible, right? For example, this is for military something or national security. So it's not allowed to overlay your signal. And in that case, how can you formulate your problem? This is the idea of transmit band and receive band and channel band. Got it? So T means where your signal, transmitted signal, can occupy. That is the B sub T, transmit band. B sub R is receive band, and many of you say that, hey, receive band should be the same as transmit band. Why we observe where in the frequency band where our desired signal is not there? If you ask that question, you are still not fully understanding the interesting characteristic of a cyclostationary signal. The cyclostationary signal has or may have very strong correlation between frequency components at here and there. So suppose you have fifth signal occupies this band. However, you are allowed to transmit from here to here. In that case, it's intuitive and also wrong to choose from here to there as transmit band and receive band the same. Actually, you can better design your system by observing the entire band. Because some signal component outside your transmit band may have strong correlation with the interfering signal or legacy signal inside your transmit band. Got it? So your so-called intuition does not work whenever you have spectrally correlated signal. If you don't observe that part of the frequency band, actually your receiver or system becomes suboptimal in the sense that you discard some information from the spectral correlation in designing your system. Why you disregard new information or some information that can be utilized? Got it? That's why we have this strange notion. And here, as I told you, if this case third band is prohibited, and you do not want your optimized signal transmit any power over that, actually, even if your channel looks like, for example, this square root raised cosine, actually, you can null out that part. In that case, if you transmit over that signal, suppose you have some channel that has null, and your signal transmits through that channel in that band, what will happen? Your signal power inside that band is wasted. And if you put that power out of that nulled frequency band, your performance will strictly increasing. So actually, this idea of slightly modifying or channel filter response by incorporating this kind of conditions of not allowed band, then actually our optimization problem itself automatically generates our result that does not transmit here. Got it? The problem or the limitation, yet another limitation of this paper is that even after we introduced this idea, myself and my research assistant didn't fully utilize this idea in simplifying all the optimization problems related to cyclostationarity. Do you remember that when you use frequency shift vectorizer, fresh vectorizer, if you, for example, have 3 pairs of modulate and Nyquist low-pass filters, but your desired signal and all your interference or your receiver can only observe less than 3/2 plus minus 3/2t period. In that case, you have some strange things, right? Because if you vectorize, sometimes you have length varying output. Of course, in some cases, you had better have that length varying vectors and matrices. However, in the optimization, actually, you can do this. What? You just always have odd numbers of Nyquist bands so that you have perfect symmetry in the frequency band when you vectorize the signal. But what you do is that you just put nulls in the channel. Then your optimized transmit signal will automatically transmit no signal over that band. And your optimized receiver will not observe that band. Or if it is allowed, then it will observe some interference so that even though the transmitted signal does not occupy that band, if there is interference strongly correlated with the desired signal in some frequency band, you can suppress the signal by using the spectral correlation. Anyway, so if you see the complete set of the papers generated by our group in this topic, you will see some inconsistency. So something good idea is developed, but not used here, but used there, not used there, but used there, something like that. Okay, that's the limitation of the paper publication by different authors and co-authors. So I was the co-author all the time, so I may be the person who has the full blame. Okay, so that's all for today, and let's continue this paper next time. So you must expect some take-home exam type problem set to be given you for the long weekend and extended weekends. Okay, that's all for today.